Thanks a lot. So yeah, I mentioned Atlas, and as you mentioned, I'm active in flavor physics in Atlas, but I will concentrate on UTFit as you asked. Do you see my mouse so that I can point to things?
Yes, we can see that.
That's good. Okay, so I'll a little bit of introduction, a little bit of mentioning of the tools, as you mentioned, the unitary triangle, and then I'll concentrate on two main parts, the standard model fit, which is our baseline fit. So I'll tell you a little bit about the constraints that we use there, and how we check for tension in our fit, and the fact that we can do prediction based on the over-constraining that we have to fit. And then I'll move beyond the standard model and what we can do there. There are basically two things that we can do, like a model independent analysis, and I'll mention what kind of specific constraints we can use for that, and then a scale analysis that considers more specific new physics model. So, you know, I'm sure you know everything about this. I'm just gonna give again, state again the obvious. So CP symmetry is violated in any field theory having in the Lagrangian at least one phase that can be reabsorbed in some redefinition of the fields. In our standard model, the mass eigenstates are not eigenstates of the weak interaction. And so we use this mixing matrix, the CKM matrix, which is by definition unitary, to represent this mixing of the quarks. This is the famous parameterization of the mixing matrix. It's based on the Wolfenstein parameterization. It's actually the Boras version. So you see here that you have the four parameters are A, lambda, rho bar, and eta bar, which is what I'm going to use. Now you need four parameters again because of the unitary nature and for the fact that some phase can be reabsorbed in the definition of the quark field. So you have to have four parameters in the CKM matrix. And this is a very useful representation because it gives you the idea of the size of the element. So it's an expansion in terms of lambda. And so you have that the diagonal elements are basically the biggest one here, of order 1. And basically they are connecting up and down quark of the same family, okay? And then as you jump between families, you have the elements of the CKM reducing, and the minimum is when you jump between first and second and third family, like in this two extreme here, where you have VUB and VTD, okay, where you're connecting first and third family. Now, if you exploiting the unitary nature of this matrix, you can write unitary expression. So you can write this kind of expression where you have three complex numbers, some that have to give 0, okay? You have also expression that gives 1, like because of the unitary definition. Now, if you take one of these in particular, so the one that is connecting the down type quark of the first family and of the third family, then we have what we call the standard, the unitary triangle expression, which is this one. Now, if you, again, you have the sum of three complex numbers. So if you sum it together and it gives you 0, you can represent them as a triangle in a complex plane. And now a complex number is this one, rho bar minus, well, rho bar and eta bar are the real number and the imaginary number. So they are the axes of our two-dimensional complex space. And this is because you're talking about the D quark and the B quark, you're actually connecting to observable, they are specific to B decays, okay? And in fact, if I expand here, like every side and angle of this triangle can be connected to a number of observable, a number of processes. And I mentioned here the main ones that I'm gonna talk about basically. And they all like basically BD decays, okay, BD processes. But to over-constrain, the idea is that you want to have as many measurements as possible. And we can also find connection to Robari-Tabar based on other observables in top of it. And we put them all together in order to over-constrain the fit, in order to be able to do prediction and to increase the testing ability of our fit. Now, the fit is called UTFit. You have this web page where we casually sometimes update our results. There's been a little bit of change. We are preparing a new paper finally, and there's a little bit of change of names. The color coding here, the red are the experimentalists, the blue are the theorists or lattice experts. So you have a little bit of a hint of, the experimentalists are from Atlas, CMS, and LHC B, and then there are a number of phenomenologists, model builder, and latticity experts. Now, the method that we use is based on Bayesian statistic. And this is just a quick summary of the overlook. So you have in the first column, you have your observables, so that what the experiments can measure. In the second column, you have the functional form connecting the observable to the Robari-Tabar plane. And then you have extra inputs. That is what you need to connect if you want the hadron level that is behind the observables with the quark level that is behind the functional form. Okay, so basically this comes from operation product expansion, lattice QCD, like several calculation. And there's also the mass at the top that it comes into play. So these are some the papers that are showing more detail the method that we're using. Now, there are, as I said, I have a number of constraints that I can use, and I start from let's say the oldest one, that one we call lab style or side constraints. And they're linked to the B physics, so the BD physics, and also to the K-on physics, but it's still connected to CP violation. So you see the connection is to the CK matrix is obvious. Now, there are different functional form that I'm gonna give to you. So I start from K-on physics because it's a little bit of the outlier. I see that you're gonna hear from Christina a lot about K-on physics. Now, the K-on physics enters via the K-on mixing. So you have this box diagram that, so delta F equal to 2 transitions. And the expression that you have here is what connects our observable epsilon K with the functional form that I mentioned. So our eta bar and rho bar. And the other terms contains the perturbative part and the non-perturbative part. And so you have as effectively as other inputs to our fit, the lattice QCD value of BK, okay, that you see here. And again, this is part of our fit that we update constantly, okay? And this is the one that we change. Of course, the experimental measurement is there since a while. Similarly, you can play a similar game with the BD and B sub S mixing. And from those, you extract the mass difference of the two eigenstates, the mass eigenstates. And here there is a lot more activity on the experimental side, because this is being measured by the collaboration, LHC B, and also other collaboration in LHC. And again, it proceeds via the box diagram. So, and this is the expression that again connects the observable with the functional form. You see there are other elements of the CKM, just like we had them here as well. So you see the other parameters of the Wolfenson parameterization. So that's important. That's why it's important to do a global fit of all these variables. And then lattice inputs. Now, in this case, we have delta MD that has a direct dependence on our rho bar eta bar parameters, while delta mass is basically used in ratio in order to improve the error. So you see how the effect of the two measurements are improved by the fact that you're using a ratio as usual. Okay. I forgot to put the inputs again. So we take this inputs from Lattice QCD. I have in the backup the table of the inputs that we are currently using. This is updated to last summer. So you'll see summer 2021 numbers. I'm currently working on the new one, but because I was on holiday, I didn't finish the new run. So apologies for this. So the third constraint that I want to talk about is this ratio, where we get directly the ratio of two CKM parameters, so VUB over VCB. Now, this is changing a little bit because now we have a tree diagram, so not a box anymore. So you have a direct decay. So clearly this is a dominant transition, and it's a B2C and a B2U transition. So B2 is going to be suppressed by CKM because you're connecting to the families that are the third, and the first. But this, because you have a tree diagram, you want to think that the new physics contribution here is negligible. So it's if you want to, we consider this the benchmark for for the fit for any model building that you can think of. Has to still comply with this kind of constraint, of course. Now, there are two ways you can look at this. You can use from the experimental point of view, you can use an inclusive analysis or inclusive analysis of semi-leptonic BDKs. And these two analyses have very different implications from the point of view of both experiment and theoretical assumption. And they need extra input from operational product sum function and or lattice QCD. And so because they are so, even if they're looking at the same observable, they're very independent in how they get to this observable. And that is the main discussion that has the main tension that we've seen in this fit since probably 15 years now. It's been changing a lot, this discrepancy, but this is the summer 2021 state of the art. I report here the VCB, the single values, basically the VCB from the exclusive analysis and from the inclusive analysis, and I report here my source, okay? And then I report here the discrepancy between these two values. Again, VUB and VCB, both the exclusive and the inclusive, the source. like for the VUB inclusive, this might change this summer because we're working on having a different determination, but this was taken from the HFLAV with a flat component that basically covered the spread of the central value for the different method that the HFLAV shows, okay? And then I mentioned here the discrepancy between, this is the reference to the discrepancy between the two values, the inclusive and exclusive. And this can be visualized by the two bands here, okay? So this is the VCB band for the exclusive and for the inclusive, and you see this almost 3 sigma discrepancy here. And this is the two bands for VUB, which used to be the biggest one. Now VCB is the biggest discrepancy. Now, then there are two bands that are showing direct measurements of the ratio. So VUB or VCB measured directly. I forgot to put the absolute value, of course, is over here. And this is rather new. This comes from a LHC paper that looks at B sub S decay at high Q square. This comes from lambda B. Now we have been excluding it so far. We're having the discussion now. I'm not sure how it's going to end, but at the moment we're discussing we have been excluding it, basically following the FLAG guidelines of excluding cases where only one determination of the lattice QCD parameters is available, which is a little bit unfair both on the lattice determination and on the experiment determination. So, but yeah, okay, that's how it is at the moment. Then if you put together like what we do, because we have a tension between these two determination, we cannot quite average them as normally. So there is that you can use a method for skeptic averages, and we implemented this method in a 2-dimensional procedure. And so the result is this yellow blob at 95% confidence probability, and the dark orange blob at 68% probability. And this comes from this 2-dimensional inflation procedure, okay? If you do the same procedure that the PDG does in averaging two values in tension, you get something very similar. We cross-check that, okay? So you get this as a central value for VCB and VUB. With very little correlation, as you can see. So we use these inputs in the global fit, okay? So of course you are like inflating a little bit the error, but you see that you're covering most of the experimental results. And then this, I mentioned here, anticipating a little bit, the results of, which is this red blob here, the results from the global standard model fit. So when I put all my, like the fit I presented in a moment. So when I put all my constraints inside, this is what I get out of the fit for these two parameters. And these are the predictions that are obtained by removing the specific parameter from the fit, and then doing the fit without this input. Okay, so you see that the error doesn't change too much. Okay, so but it's better than the input that we get, of course, because the fit helps us identifying the specific. Of course, if you want to notice and want to learn something from the fit, the fit is not helping you too much, because it points to this corner here where it points to an inclusive VCB and exclusive VUB. So it doesn't help you to disentangle between possible systematic effect between inclusive and exclusive. So this is a very much open discussion at this point. Now, if I put all my 4 left style constraints together, I get this, we call the sides plus epsilon K fit. And you have this kind of determination. This is the error between 7 and 10% on rho bar eta bar, which is already rather good because we made lots of improvement in the last years on the B the B related determination, and also on the lattice QCD, of course. Okay, so this is even if this is a old style analysis, it has been improving in the past years, of course. Okay. Now, the new style analysis, if you want, but it's also old because B factors are now old, is involving the angles. Okay, so from the B factory and now LHC B, we get information on the 3 angles of the triangle, and this is how they look if you project them in the rho bar eta bar plane. Okay. Now, the most famous one is, of course, sin to beta, and this comes from the time-dependent analysis of the time-dependent asymmetry of the B to J side K0 final state. And this exploits the CP violation in interference between mixing and decay. Okay, that means that a B0 decays in a final state, or can oscillate and then decay in the same final state. So the important thing is that you have a common final state between accessible from B0 and B0 bar, and then you create basically the possibility of interference. And of course, CP violation is based on the fact that it's possible to have interference. And this time-dependent asymmetry can be written like this, like the probability of B minus B bar over the sum. This is the classic definition. Of course, there can be a minus difference depending on the experiments. But in terms of actual observable, you can write it like this, where you have a sine and cosine terms that depends on the frequency of oscillation, basically, and then like a coefficient in front of them that is modulating this oscillation. And if in this case of what we call the golden mode, the J psi K0, basically your asymmetry is simplified in this, where you basically directly see your coefficient here as sine 2 beta. Okay, and so you extract sine 2 beta in a very nice and clean way. Now, the B to J psi proceed via a tree diagram, dominant tree diagram, and the interference is with the box diagram of the mixing. So again, you have something that depends on the mixing. So the box diagram that I already mentioned when I mentioned delta MD, delta mass. Now, I use this all plots because it's rather spectacular and shows the rho asymmetry, the time dependent in function of the time. This is actually the difference between the time of the decays of the 2 Bs that you produce in pair in B factors. Okay, but you see how beautiful the oscillation is. And you see here the latest compilation of results from HFLAV, you know, LHCb is now producing numbers that are very competitive with the B factor, which is really impressive. Now, for our input, what we do, we only use J psi K0. So this is what you see here. HFLAV uses also other inputs. So what you see here is different from what you see here, because I only use J psi K0. And this is because there is, I mentioned that B to J psi K proceeds via a tree diagram. But of course, there is a subleading penguin diagram as well. And so you can estimate, and that would shift your observable in a way. Okay, the fact that you directly measure sine 2 beta can be affected by this tree of penguin diagram. So there is a way that these guys published a while ago, a lot ago, that is a data-driven uncertainty. This number is not in this paper. We keep redoing this analysis to update the number with the latest inputs. And now this is the theoretical uncertainty that we're using, and we also use a shift in the number. So this is what the HFLAV obtained from all the experiment, and this is what we actually use as input. So a little bit inflation of the error and a shift in the central one. Okay, and this is our way to estimate the theoretical uncertainty on this measurements. So the other angle is alpha. Alpha is a little bit more complicated. The idea is the same. The idea is that you are considering CP violation in interference between mixing and decay in this final state with two pions, and we see it in two rows as well. So this is the main three diagrams that dominates this decay. And if I consider only the tree diagram, this would be exactly like the sine to beta measurements, and I would be able to measure sine to alpha in a clean way. Okay. However, in this case, because you have in the tree, you have a B to U transition, which is rather suppressed from the CKM point of view. So you have a branching ratio that are rather suppressed at the order 10 to the minus 6 to the 10 to minus 9, whereas, well, 10 to minus 6, with respect to, for example, J psi K0. The penguin diagram, you cannot be sure that is so suppressed with respect to the tree, okay? And so if you consider, in this case, also the penguin diagram, your actual observables, what you measure from the experimental point of view, is not exactly clean as in the sine to beta case, but it's a little bit dirtier and has this like more complicated relationship. And so what happens, you have to disentangle this relationship in order to get to the alpha, to the pure theoretical parameter that you need to include in the fit, okay? And to do that, you need to do an isospin analysis, which basically means that you need to look at all the branching ratio of B0 and B0 bar. I don't know why I lost the B bar here. In all the pi, well, in this case, I'm talking about pi, but it would be the same in rho, final state, okay? So these are the three final states. They are connected from isospin relation, and basically the one that is a pure isospin state is pi plus pi 0. So you have this common side, and then you create these two isospin triangle using the B or the B bar, the CP conjugated, if you want, decays, okay? And by doing this construction, you basically are able to measure alpha effective and the shift in order to get to alpha, okay? So instead of measuring only one, having one observable, you need to have all, let's say, the measurements of all the branching ratio, and also in principle the asymmetries, okay? These are the results, and I show here the results from HFLAV, the latest ones, in both the pi case and rho case. The rho case is similar to pi. It's a little bit more complicated, of course, because while pions are scalar, rows are vectors, so you have to do also an amplitude analysis in your experimental analysis. But I'm not going to go into details there, I don't have time, but this is the C component and the S component, so the coefficient of the cosine of the oscillation or the sine of the oscillation, if you want. And you see how the two cases are rather different. So you have that the pi case is already very different from very outside zero. So you actually have a clear measurement of CP violation in the pi case. So this is 0 in this plane, and this is where all the measurements are. While in the RoRo case, this is 0 and this is your measurement. So in here, you don't yet or still, or yeah, I mean, yet have a clear evidence of CP violation. You start having some effect, but it's not clear yet. Now here there is a little bit of difference in the relative effect of the various final state, okay? And so and that what gives the different, if you want, sensitivities. I'll mention how we include alpha in the fit in a minute. I'll go a step to the last angle first, and then I give you the inputs that we use for both alpha and gamma. So gamma is the last angle. Gamma doesn't come from, again, from CP violation, but is the CP violation in the direct one. So in the interference between the two decays, two amplitudes that are contributed to the same decay, okay? So this is, again, something that is based on a tree diagram, okay? So this is our second constraint, together with the VUB over VCB ratio, that depends on a tree diagram. And so that's going to be, I'll mention this later as well. Now here you're just measuring branching ratio of B to D K decays in various forms. So D star, K star, D, K star, D star, K, and so on. There's no time dependent analysis. So it's just like this number of events that you get. CP violation always has to have to come from an interference between amplitudes. So as I mentioned, you have to have two ways to get from your initial state to your final state. And in this case, there are three diagrams. And you see, if you want, the two paths that your decay can take, and how they can interfere. The interesting bit, or the negative bit, if you want, the problematic bit, is that you have one of the two that is depending on VCB, so it has let's say a lambda 2 contribution, while the other depends on VUB, so it's more suppressed, it's a lambda 3 contribution. Okay, so here you have like you are in a disadvantage because you have this that takes down the possibility of interference. Okay. So what happens is that basically, if you write the amplitudes and you write the amplitudes of one with respect to the other, what happens is that you see explicitly the dependence on your gamma phase. You have the dependence on some strong phases, okay? But you also have the dependence on this RB parameter that I expand here, which is an amplitude ratio, effectively, that depends on rho bar, eta bar, but also depends on hadronic contribution, which are channel dependent, okay? And this effectively, because it's just in front of the gamma term, is basically limiting your sensitivity, okay? So this is what limiting sensitivity, and depending on the various channel, it can be harsher or less harsh, okay? So these are some numbers, and I'm gonna, so if you have a 10%, for example, for decays, okay? With the K plus. And so when you do an analysis in general, there are different methods that you can use to measure gamma, but most of them will also give you this ratio as part of the observables. And some methods are more sensitive to, they're even more sensitive to this ratio rather than to gamma. And they're still they're still very useful because, of course, these are key components. So you have to extract all of them, okay? Now, this is the table from HFLAV. I'm sorry, I forgot to mention this, but you see here. So, and you see how there is a gamma value that comes from a global analysis they've done, and you have also the various R and the various strong phases. Okay, so this comes in a global fit altogether. Okay, and you have here an example of the extraction of gamma and the extraction of the two-dimensional in gamma and the RB. So what we use now for alpha and gamma, because the HFLAV has started to produce their own average. In the case of gamma, we are using directly the HFLAV average because there's so many analyses that it's really, really hard to make sure that you're using always the latest ones. So we gave up, basically. We cannot keep up with the experimental inputs. And I put here the comparison with the prediction, where I run the fit without using gamma as an input. And so like they are amazingly one on top of the other. So gamma is amazingly standard model at this point. For the alpha, HFLAV does give a result. We still use our methods because it's to us is more accurate, and you see these are all the probability PDF from the various final state. So I mentioned pi, I mentioned rho. There's also a less powerful analysis because it's still like kind of old and low statistic of rho pi. And you see that you have different distributions. The key point that we like is that the pi exclude the zero, as I mentioned, which is a reason for discussion with other groups, let's say. But so we keep this analysis going, and because it's relatively straightforward. But you have to consider that we have a slightly different input for alpha in our fit. And again, I compared this with the UT fit prediction that comes from the entire fit without using the alpha constraint. Okay, so the yellow is our average that we are using as input. Now, if I then put together, then I have my angle fit. So using only the angles measurements, and so alpha, beta, gamma, you see here. And you see that the precision is now at the level of the pre-B factory fit. Okay, so it's rather impressive. Now, if I put the all the 7 constraints that I mentioned together, I get this. Okay, so this is the updated fit. Where you have the precision of rho bar, eta bar. You see there's like a small point. I can zoom in so that I can see the 2 areas. So the smaller one is 68%, is bigger one, 95% probability. While in general, the area are all at 95% probability to show you better. Okay. So this has become rather precise. And if you look at the single areas, you see how there is an impressive agreement between each of the constraints. Okay, I dig up a 2004 plot just for my pleasure today, and this is the comparison, and you see how big it was when I personally started to do this kind of fits, and it's rather impressive. There are some different configuration that people are also looking at in different configuration. There have been several papers from other collaborations also coming out with this different configuration. So of course, you've already seen the angles only. You have already seen the sides plus the K mixing. You can have this is a Burra's idea of having this universal unitary triangle, or you have the tree only. And I did mention already when I presented the various constraints how BUB over BCB and gamma are dependent on 3 processes. So they are your reference, if you want, for model building, that you know that new physics is not expected to enter this kind of fit. And you can see here that the errors are compatible at this point. Of course, you have also the mirror solution on the third quadrant. Now, to check the fit and how it is compatible, I'm really slow. I'm sorry about this. We do compatibility plots. Basically, we remove the specific observable from the fit, and then we check what kind of prediction comes from the fit without that, and we label the various areas as 1 to 5 sigma, if you want, of tension with respect to the input that you want to consider. So an experiment. So if you plot this with a given global fit, without using, for example, the alpha input, then the alpha experimental input is in a point where here you have the error on this input, and here you have the central value. Okay, and so you see how alpha and gamma are amazingly spot on. There is a little bit a tension since a long time on sine to beta, so you see that is a little bit more than 1 sigma. And there is the expected tension that I already mentioned between with VUB and VCB. Now, here I have the cross here, which is the average that I'm using. And this shows almost perfect agreement, of course, because I'm inflating the error to take into account the discrepancy. But then if you look at the various specific inputs, you see again the discrepancy that we saw in the 2-dimensional VUB over versus VCB plot. Okay, so there's nothing new. It's just our fit giving back exactly what I already showed you. Now we can play this game for all the observable. You have your observable, the measurement, and then the prediction obtained by removing that observable from the global fit, and you have the kind of tension that you get. So you have like very little tension, you have some tension from sine to beta, epsilon k, and then VUB over VUB and VCB that are showing this tension, but basically on the specific either inclusive or exclusive values. Now, what we can do, we can also do an analysis adding extra degrees of freedom to our fit in order to account to possible very generic new physics. And so this comes, you can parameterize this generic new physics like this. You might imagine to have a coefficient and a phase that can contribute. And basically what you can do, you can associate an amplitude and a phase to each delta F equal to 2 transitions. So each meson mixing, okay? So the B sub D's, B sub S, K on D's and so on, charms and so on. And then you just reinterpret, okay, then you just reinterpret all your observable, take into account this shift either in amplitudes or in phase for the angles, okay? So this is your how the amplitudes is changed with this new physics generic contribution, okay? Now this is like a added this table just to say what are the observables that we're using and how they connect to the new parameters. So in particular, you still have rho bar eta bar, but you have also the new physics contribution in B sub D or B sub S and in the kaon system. Okay, so B sub D, B sub S and in the kaon system. And there are specific constraints that will link to one or more of these parameters, okay? And here you have a little bit of summary on how these parameters are changed. The observable are changed by this new physics parameter. We also add new constraints. In particular, the semi-leptonic asymmetries are useful because they are connected, sensitive to new physics effect, both in the amplitude and the phase of this new physics effect. And this is the numbers are taken from HFLAV all over. And then we use the BS to J sci-fi angular analysis, time-dependent analysis that gives the phi s angle. Okay, and this is again the latest one from the average from HFLAV. Again, there's a tension here, and the HFLAV has been applying some kind of scaling because there's a kind of significant tension in CMS and Atlas, not directly in phi s, but more in delta gamma s, but still it's kind of interesting. Now we can run our fit again, and again we can extract rho bar eta bar. Now here I show only the areas corresponding to the constraints that are not affected by new physics, just because it's easier, but the others are also in, okay? And you see that at the end, the precision is less good, of course, because you're adding extra degrees of freedom to your fit, okay? But it's still kind of impressive, and the fit does choose exactly the same region that the standard model fit chooses, okay? What you can do, you can then look also at the new physics parameters, of course. And I put this red cross, which is the standard model. So it's of course 0 or 1 for the phase and the amplitude, okay? And you see how this is a rather recent change where now the B sub S is so precise that it's really closing on the standard model. And now there's a little bit of a tension on the B sub D side, which is something that is happening in the last 2 years. We can also reparameterize this. I show here because it's also useful to visualize, reparameterize these new physics parameters in terms of the new physics phase, but here I show the ratio between the new physics phase and the standard model phase. And this gives you a little bit of an idea of how big the new physics contribution can still be, even if our fit is actually very standard model at this point, okay? And so you see that, of course, it's very limited in the B sub S because we see that now is rather precise, but there is a little bit more space, let's say 30% possibility for the B sub D of new physics contribution still, even with this very precise fit. Now, the last thing that we do is extracting a new physics phase. And so like we write all the possible operators that in the more generic effective Hamiltonian, even the ones that would not appear with different chiralities with respect to the standard model. And then these are the operators here. And then these operators will be weighted with the Wilson coefficient. And what we can do, we can extract this Wilson coefficient from the field, let's say their probability distribution, of course. And this can be linked to, they can be factorized in these terms, where you have the Flavour coupling, the loop factor, and the new physics scale. So you see that the coefficients are inversely proportional to the square of the physics scale. So if you have a bound on the Wilson coefficient, as we can get out of fit, we can have a bound on the physics scale, okay? So if you have an upper bound of the physics coefficient, you have a lower bound on the physics scale, which is interesting. Of course, then you have to assume some behavior of the new physics. So I didn't do this one because it's a little bit more complicated, and I didn't have time. But like these two, we currently do every time. So a generic scenario where you have the flavor coupling equal to 1 and an arbitrary phase, and the next to minimal flavor violation scenario, where you have a flavor standard model like and still an arbitrary phase. The loop factor, so this one here, okay, that is the coupling between the standard model and the new physics. And of course, what we do, we use this loop factor equal to 1. That would imply strongly coupled new physics, which is, of course, not realistic at this point. But what happens is that it gives us the possibility to then consider all the other cases in a very easy way. And I'll mention this, because you just can multiply the limit that we get by your loop factor, and you get the limit in that case. Okay, so it's just for clarity, if you want. So of course, if there are no new physics effects, you have a lower bound on the new physics scale. Okay, and so this I did update, and I didn't have the plot with me on holiday. I'm sorry about that. But it hasn't changed the substance of the analysis. So basically, these are the bound on new physics scale based on the various systems. So delta F equal to 2 systems. And you see that in general, the C4 is the dominant one, the Wilson coefficient of the Q4 operator. And in general, the K-on system, so this bright green one, is the dominant one. Of course, you have to find the highest one to get to the limit. And that's in the two scenarios that I'm giving you, the generic and the next to minimal flavor violation. And so to translate this, it says you have a very, well, in the generic one, of course, you have a very strong statement for the lower bound on the new physics case. This is the example for if you want to translate this with a strong coupling to something with a weak coupling between the standard model and the new physics, then you have something that is still rather strong. However, for example, in next to minimal flavor violation, you get something that is a lot weaker. And if you consider a weak interaction, or a feeble interaction, like we like to call it now, you get something that is somewhat at the level of what LHC can achieve now. So this gives LHC some hope to, for example, for a direct measurement discovery. So to conclude, with this global fit, we can test the consistency of the standard model and the CKM mechanism. We can compare inputs and indirect determination. We can do prediction. And we always update regularly with all the latest results. We can do the model independent fit, both in the generic way and in the scale analysis by considering specific models. And LHC B and LHC in general, and also Belle II, will keep contributing and will keep contributing to this analysis. Now, the current situation is that the standard model is shows a very good consistency, and there's the only real tension at the moment is the usual discussion that we're having since a long time on the semi-electronic results in the comparison between inclusive and the exclusive. If you run the new physics analysis, you still have possibility to have new physics that is not excluded at the level of even up to 30%. I forgot to update this, I think. Okay, sorry about that. But if you look at the scale analysis helps you in the sense that, of course, it excludes a generic scenario, it excludes a strong coupling, but it still gives you some idea that you could have a direct discovery at the LHC with a weak interaction between, weak coupling between standard model and new physics. And of course, there is, I left out completely the uptype sector, so the D sector at this point. I do include it in the scale analysis, but not in my other, and that's also can be very interesting at this point. I think I can finish here. Sorry for, I think I'm late.
Oh, thank you very much, Marcella. That's okay. We have some contingency on the agenda, so
okay, sorry.
No problem. So
I enjoyed it too much. Yeah, sorry.
No, there's a lot to cover as well. So, are there any questions for Marcella? Please raise your hand or open your mic.
Jim, can I ask one quick question?
Sure, Namit.
Hi, Marcella. I was just wondering that the fit results for the Wilson coefficients that you showed, do you assume, what do you assume for the, these ones? What do you assume for the loop functions when you actually fit? Here you have, so.
Yeah, so basically this, and what we assume one. And so what happens is that you implicitly assume strongly coupled new physics, which we all agree is not possible, okay? So, but what happens is that because at that point you would have just the multiplicative terms. So then what you do, you can just multiply your desired loop factor by this, by your, but the L equal to 1 limit. You see what I mean? So so for example, if I multiply 0.03 by this, I get this, okay? So whatever you want to do, you can do it by just a multiplication, and that makes things easier. Does it make sense?
Yeah. Meaning I was just, this is the translation. I think I missed the last line in the slide. Okay, thanks.
Yeah, no, I probably didn't mention that. It's small prints.
So maybe I can ask a question, as I don't see any others at the moment. In the alpha averaging, you have this somewhat different result from HFLAV.
Yes.
And this is, if I understood, this is due to your priors saying that we know there's CP violations, so 0 and 180 are excluded.
Yeah, we basically cut away the 0, right? You see that here, this dark blue, it's dumped here. Yeah. Yeah. So, it's also an effect of the Bayesian approach, of course. Yeah.
Yeah. So I was interested that there's this 7-degree shift or 8-degree shift, sorry, between the central values. So is there some sort of heuristic explanation of what's happening, even though you're affecting things at the edges of the distribution somehow?
Yeah. So I don't know. Okay, there is a little bit. I don't know this one. I asked myself, and I promised myself that I was going to do some tests, because what I can do, I do have the possibility in my code to run a, it's not exactly a frequentistic one, but I can remove this dump, and I can run a more frequentistic similar approach. And I regularly do it, but it's a while that I haven't doing, and I just this is kind of like it's the new thing from HFLAV that they're producing this average. So yeah, I should check that. I don't know what it's a kind of a big, I agree, it's a big discrepancy now. There is also a little bit of inconsistency between the two HFLAV groups. So I'm also not, because the inputs from this have to be taken from the unitary triangle group, but also from the rare decays group, because you need all the so I know that they're working separately, so I'm not 100% sure of if what I have here is actually exactly what goes inside. There's for example, pi0 has been changing a little bit, rho 0, rho 0. So, and also rho pi, I mean, rho pi is like super complicated analysis. So there could be lots of small things that might make, but yeah, I agree, I need to check because I'm not convinced.
Okay.
Yeah.
But no,
the prediction is just in the middle. So the prediction doesn't help to validate mine or HFLAV.
No, both are compatible.
Yeah,
but yeah,
exactly.
I understand if you're taking from the rare decays, the branching fractions and things, and if it's slightly different, then this could have an impact with these isospin relations.
Yeah, I could check this our other analysis, just like using the same fit, but instead of using the amplitudes, using the branching ratio. That usually gives something that is very similar to this frequentistic one. So I should try that. That's a good point. Yeah.
Okay. Any other questions? If not, I'm going to indulge myself with a second one, if that's okay. We've heard a bit about during this school this Cabibbo angle anomaly. So I was just wondering if you started to look at all at the sort of general unitarity constraints. I know you do the charm ones, but have you looked at the Cabibbo angle as well?
Not particularly, to be fair. What so you're talking about VUD, VUS.
So it's really the VUS is the one that people are interested in.
Yeah, we updated it, but we haven't reflected too much on that yet. We did change the inputs a little bit in order to basically use only VUS, but yeah, no, I haven't looked into that.
Okay.
Yeah, that's a good point as well. I think that will be in the paper. Like, I think we are right. The paper that we're writing will address that, but I'm not sure about the discussion ongoing, so I cannot quite comment at the moment. Yeah, but yeah, we do use unitarity though, of course. So yeah.
Sure. Okay. All right. So I think we thank you again